Okay, fine. Now I have made it on. Okay, fine. Okay, so everything is clear for everyone. I repeat the method one very quickly. We have a open loop transfer function phi divided by s into s plus 1. So finding the stability of closed loop system using Nyquist plot is the question. So the first and foremost thing is like represent the poles and zeros on the s plane. Then the conventional procedure is map the entire right half of s plane onto the gh plane. But here we have a pole at origin, and even if there is a zero at origin, the same method one will follow. So when we have pole or zero at origin, we need to make a selection. Okay, whether to include this in the right half or to exclude this in the right half. So we have the first method where we are including that in the right half of a plane by defining EFA in this fashion. Okay, that is minus 92 minus 182 minus 270. So when we define our S plane in this fashion, it means we are including it in the right half of entire S plane. Then in method 2 what we do is we exclude that pole or zero at origin, okay, from the right half of S plane. So this is second option. Let me just draw a line. So what is mean by excluding? So excluding is you are defining your entire right half of S spline in other way. Okay, in other way. So how is that? So path BCD goes like this, then path DE, then we have path DE, then path EFA. Path EFA is now in the other direction. Fine. So the definition of S will remain same. Okay, path EFA definition of S will remain same. That is limit as R tends to 0 e raised to J5. But phi is now changing from minus 90 to 0 to plus 90. Okay, minus 90 to 0, then plus 90. So this is the definition of EFA. In the exam, you can use any one of the method. Okay, any one of the method, and your result will be same at the end. So this is about considering poles or zeros at origin. So let us proceed how to solve this. So these two cases are important. So next we will take up the numerical. So here first I will solve with method 2 where we have excluded it from the right half of S plane. This is the easiest option. Then I will come to method 1. So first mark the S plane, poles and zeros. Then represent the entire right half of S plane by choosing EFA such a way that we are excluding the pole at origin from the right half. So this is BCD, then EFA. So altogether ABCDEFA represents our entire right half of S plane. Then draw GH plane, write TLGH and imaginary GH. The first step is to map the path AB. So to map path AB, substitute S equal to J omega, then we need to write GH of J omega, separate out gain and phase now. So gain is given by pi divided by square root of omega square into omega square plus 1 square. Then phase angle is 1 divided by tan inverse of omega by 0, the phase angle contributed by this factor, then tan inverse of omega by 1. So tan inverse of omega by 0 is 90. When it goes to the numerator, it will become minus 90. The other factor is minus tan inverse of omega. So first is point A, where we write limit as omega tends to 0, gh of j omega. So when I write limit omega tends to 0, this denominator fact is 0. Therefore, gain will become infinity. Gain will become infinity, and let us see what about the phase angle. Phase angle is minus 90. and tan inverse of 0 is 0. So phase angle is minus 90. And when omega tends to infinity, the denominator is infinity, so the gain is 0. What about the phase angle? Phase angle is minus 90 minus tan inverse of infinity. So both together it is minus 180. So this is quite different from previous numerical. We have initial gain as infinity, ending at an starting at an angle of minus 90 degree, then gain equal to 0, ending at an angle of minus 180 degree. How do we draw it on the GH plane? So observe carefully, it is my infinity minus 90 degree starting point. So how do we represent that on the GH plane is the question. So what we do is we consider the minus 90 degree line, and from there I consider minus 90 degree line and I start with the dots showing that it starts somewhere from infinity and ends at 0 magnitude at minus 180 degree. Okay, started somewhere at infinity with minus 90 degree angle and ended at 0 with minus 180 degree line. So this is mapping of AB, which we can say it as A dash B dash also. Next, mapping path BCD, we have limit as r tends to infinity, r into e raised to j theta, where theta is changing from 90 degree, 0 degree, minus 90 degree. So this is path BCD. So when you substitute this s here, it is gh of r into e raised to j theta equal to pi divided by limit as r tends to infinity, r into e raised to j theta into r into e raised to j theta plus 1. So r is much greater than 1. You can follow the same previous procedure. So what we get is limit as r tends to infinity, it is r square e raised to j2 theta, because this one is eliminated. So only there is r e raised to j theta, r e raised to j theta. So since r is tending to infinity, gain obviously will become 0, but phase angle will be minus 2 theta. Minus 2 theta. So minus 2 theta means minus 2 into 90 degrees, minus 2 into 0 degrees, minus 2 into 90 degrees, plus, minus 90 degrees. I repeat, this 2 theta, when it goes to the numerator, it will become minus 2 theta. So wherever we have theta, we need to substitute all these three angles. So minus 2 into plus 90 degrees is minus 180 degree. Minus 2 into 0 degrees is 0 degrees. Minus 2 into minus 90 degrees is plus 180 degrees. Gain is anyhow 0. So it will represent the origin only. It will represent the original only. So BCD is mapped as B dash is C dash and D dash. So you can also observe that there is a continuity. This minus 180 degree ends at minus 180 degree. Path AB is ending at minus 180 degree. Path BCD starts with minus 180 degree. The continuation. Next is path DE. So path DE is without any doubt mirror image of path AB. So it means it starts with somewhere at infinity at an angle of minus 270 degrees, then ends at minus 180. So the mirror image. So next, the last path left is EFA. Path EFA, where we substitute S as limit r tends to 0, r into e raised to j phi, where phi is minus 90 degrees to 0 degrees to plus 90 degrees, because we have taken in this fashion. So let me substitute S in the open loop transfer function. So it is limit as r into e raised to j phi, limit as r tends to 0, phi divided by limit r tends to 0. Wherever you have S, just substitute r into e raised to j phi. So this solution is very simple. It's not much complicated as it looks. So wherever you have r, you just substitute 0. That's the solution. So first step itself, we can eliminate this r because it is 0. So phi divided by 0 e raised to j phi is the expression what we get. So gain is infinity, phase angle is minus phi. Then substitute the phi values. What we get is infinity gain. Then this is plus 90 degrees to 0 degrees to minus 90 degrees. So it means the path EFA is mapped with a magnitude of infinity, but the angle of that line is changing, line or curve is changing as plus 90 to 0 to minus 90. So how it looks on GH plane? So it gets mapped something like this, an infinity curve which is changing its angle from plus 90 to 0 to minus 90. Now mark the minus 1 plus j0 point, which is the origin for 1 plus t of s h of s, and check the stability. So obviously there is no encirclement around minus 1 plus j0 as it has ended at our origin. So what we can write? Z equal to p plus n, the Nyquist criteria, and p is equal to 0 here because we have excluded this pole from the right half. So therefore p is 0, no encirclements, n is 0. So p z equal to p plus n, it is 0. Okay. So when z is 0, it means no characteristic root. It means no characteristic root or no roots of the characteristic equation lies in the right half of S plane. Lies in the right half of S plane. Therefore, you can say closed loop system is stable. Closed loop system is stable. Fine. So just glance this numerical arms.
Sir,
Yes,
instead of including and excluding, can we not add a pole or add a zero to shift the S-plane this side?
that can be done, but that won't be easy. You need to make a say modification accordingly in your solution also. I mean that solution will not be straightforward as it looks like this.
Okay, sir.
Okay, so there is a way that you have to add a pole. You can add a pole or you can add a zero, but the effect of angle contribution should be cancelled by its counterpart. Suppose if you add a pole, it makes some angle contribution, then you have to add a zero to cancel its angle contribution. So that is something advanced. That will come in design part. So let us not bother about that. This is much easier than that one. Okay, so look at the answer once again. Those who haven't understood the theoretical background, you can still solve this numerical. So what you need to do is you need to understand how the substitutions are made. So if you are able to do that, the final step is to find z equal to p plus n. Okay, so I hope there is no doubts. Anybody has any doubt? Glance this solution once again. So we'll come back to method 1. We'll go for the method 1 and let us see how it is different from the method 2. So this is method 1 where we are including the pole at origin in the right half of S plane. So I repeat once again, in the exam you can solve by any one method. The answer will still remain same. So this is pole and zero location. So now I have taken the EFA in the other way. I'm including the pole at origin in the right half of S plane. So path BCD is same, path AB is same, fine. So path AB, path BCD, and path D all are same. So what do we get is we get the same mapping as the method 2 for path A, B, C, D, E. Only path EFA is different. Okay, only path EFA is different for the method 1. So we have to write for path EFA. So let us see how to do it. Path EFA, I will define path EFA as s equal to limit small letter r tends to 0 when r into e raised to j5. So phi is changing now from minus 90 degree to minus 180 degree, then to minus 270 degree. Okay, then follow the same steps. Only phi is different now. So limit as r tends to 0, small letter r tends to 0 equals to phi divided by limit as again small letter r tends to 0, r into e raised to j5, and r into e raised to j5 plus 1. So this r will be 0. So again you have phi divided by 0, which is infinity. Then e raised to j5 will become minus phi. So infinity minus phi is all will become plus now. Plus 90 degree plus 180 degree, then plus 270 degrees. So this is a curve with infinite magnitude whose angle is changing from plus 90 to plus 180 to plus 270. So how do we draw that? So let me show you by drawing the GH plane. So path A dash and B dash are same. B dash, C dash, D dash are same. That is BCD. Then D is also same, which is mirror image of AB. That is also same. But what is E of A is it comes in the other way now. So we have to draw a curve whose radius is having infinite magnitude and its angle is changing from plus 90 to plus 180 to plus 270. And now, since the radius is infinity, obviously it will encircle minus 1 plus j0. So angle can be read in both ways, clockwise, anti-clockwise. So this is infinity. This will have a magnitude of infinity from the origin. So the mapped path of EFA is this one. E dash, F dash, and A dash. So what is Z equal to P plus N now? Okay, we need to evaluate Z equal to P plus N for stability. So since we have taken this pole at origin in the right half, okay, right half of S plane, our P will become 1 now. Okay, so P is nothing but the right half pole of G of S, H of S. So it is this you have chosen. And what about the encirclement? See, this is anti-clockwise encirclement around minus 1 plus J0. Therefore, our N is minus 1. So finally, we have 1 minus 1 equal to 0. Therefore, Z equal to 0. And hence the closed loop system is stable. Fine. So only path EFA is different here. That has been mapped like this. And the P, the right half of pole P is equal to 1. And N is the anticlockwise encirclement. Ultimately, it will give you Z equal to 0, which means there is no characteristic root lying in the right half of S plane. Therefore, Z equal to 0, closed loop system is stable. So in both the cases, we end up with the same answer. So that is the conclusion. Any doubts, any clarification? So if there is no doubts, we'll move on to the next numerical. Is it visible, Abdul?
Yes, sir.
Take up the next numerical. Using Nyquist plot, find the range of k for which the closed loop system is stable. for which the closed loop system is stable, given OLTF is k divided by s into s plus 1 into s plus 2. So this is a different type of numerical. How to solve this? Just give a thought on this for 2 minutes. They have asked us to find k. Okay, so let us see. So first step is draw the S-plane. Then represent poles and zeros. Then draw the right half of S-plane. So now I'll follow only one method. I will exclude the pole at origin from the right half of S-plane. So P is 0 now. Now go start mapping. So draw GH plane. So path AB, substitute as equal to j omega. So point, before that point A, we need to substitute as equal to j omega and find the gain expression, that is omega. I have taken it outside the square root, and inside the square root it is omega square plus 1 and omega square plus 4. Then what is phase angle? So phase angle is minus 90 degrees minus tan inverse of omega by 1 minus tan inverse of omega by 2. So map point A. So point A will be mapped at the infinity gain and an angle of minus 90 degrees, because this is 0, this is 0. Then map point B. So it is k divided by infinity, which is 0, and angle contribution is minus 90, minus 90, minus 90. So therefore it is 270. So starting point is at infinity with minus 90 degrees, ending point is 0 with at an angle of minus 270 degrees. So it goes something like this. Next map path BCD. So path BCD in most of the numerical, it has resulted in origin. So keep that in mind. So limit as capital letter R tends to infinity, R into e raised to j theta. So it has resulted in origin, but angle is minus 3 theta because there are 3 poles. Okay, because there are 3 poles, I am skipping some steps because we were already familiar with this. So we have minus 3 theta as the angle, and each theta is to be substituted now. Okay, so how do you substitute? We have plus 90 to 0 to minus 90. So minus 3 into plus 90 is minus 270, then 0, then accordingly it is plus 270. But since it is a 0 magnitude, it doesn't make much difference. So again we have A dash B dash, then B dash C dash D dash. Then part DE is mirror image of path AB. So how do you draw the mirror image? It's something like this. And then path EFA. So define what is path EFA. Okay, it is limit as small letter r tends to 0, r into e raised to j5, where phi is minus 90 degree, 0 degree, plus 90 degree. Then gh of r into e raised to j5. So when you substitute r equal to 0, the pole at origin will cause the magnitude to become infinity. and angle is again minus, angle is substituted, and it will become plus 90 to 0 to minus 90. Please evaluate this part. I will leave it as a work for you. So when it is plus 90, it starts from here, then 0 minus 90 here. So next the question is whether it is encircling minus 1 or no. So for that we need to find m. We need to find m. So how to find m? So you have to find omega p, that is phase crossover frequency, by equating gh of angle of gh of j omega to 180 degree or minus 180 degree. That is this particular point. So now equate my phase angle expression to minus 180 degree. Then when you solve it using calculator, directly you will get omega equal to square root of 2 radians per second, or 1.41 or something around that. So we got omega p as square root of 2 radians per second. Now find the gain at this frequency. That is m equal to gain of gh of j omega at omega equal to square root of 2. So gain expression is k divided by omega, square root of omega square into omega square plus 4. Substitute the square root of 2. So square root of 2 here, then square root of 2 square is 2 plus 1, then 2 plus 4. So altogether it becomes square root of 36, or k divided by 6. So once you get m as k divided by 6, we still don't know what is k. But how nicely we can modify this into our conclusion or final answer. So for stability, everyone knows Z should be equal to 0. So what is that? Z is equal to P plus N. So P is already 0. What should be N? How many N circles should occur here? To get Z equal to 0, N should also be 0, which means there shouldn't be any encirclement. Therefore, M should be less than 1. So if this M is less than 1, then only there is no possibility of encirclement. Right? If M is greater than 1, then there will be encirclement. This point will move somewhere beyond minus 1. But if M is less than 1, it will stay within this region, hence there will be no encirclement, therefore N will be equal to 0. So therefore I will put the condition that M should be less than 1, and accordingly K by 6 should be less than 1, or K should be less than 6. Okay, or K should be less than 6. Therefore, the range of K for which system to be stable is K should be greater than 0, that is positive, and it should be less than 6, so that no encirclement will occur and Z will remain equal to 0. Fine. So that's it for today's class. We will continue with the other numericals, the next topic, that is Bode's plot, in the next class. Ganesh, is there any meeting? Sorry, is there any class now?
Yes, sir.